Welcome to Part 3 of Module 201B on calculating sine wave values. We now know how a sine wave is generated by passing a conductor through a magnetic field, and we also know how to calculate the frequency of the system being generated. Now we're going to look at actually calculating the different values that we see inside that sine wave. Now, since the angle of cutting on that conductor is constantly changing inside a rotating conductor, we also have this constantly changing electrical field happening. Now the trick to it is how can we calculate exactly what that value is at any point in time? But here's an interesting thing. Have you ever wondered why it's called a sine wave? Now that we've learned about trigonometry, it's safe to tell you that the sine wave is all based on the vertical aspect of how high that voltage has come off of my reference line. So it's all about the vertical aspect of the generation. So the phasor itself, the length from the center all the way out to wherever that is generating, we only see that twice during the sine wave. Once at 90 degrees and once at 270 degrees, because that's when they have the maximum vertical value with no horizontal value. Every other point inside that sine wave is graphed out using the sine value of the angle that that conductor is cutting compared to zero. When we are looking at a sine wave and considering the revolution of a conductor through a magnetic field, there's a couple of different terminologies that we need to become aware of. The first terminology is what's peak value. Peak value is when the conductor is cutting it perpendicular to the lines of force, therefore we're generating our maximum amount of voltage possible. It happens twice during a cycle, once at 90 degrees and once at 270 degrees. The other term that we need to understand is the term peak to peak value. And that is the maximum distance that we can have between our two peaks. So if we're to measure a value at 90 degrees and measure a value at 270 degrees, our peak to peak value would be the difference between both of those. Keep in mind that my 90-degree value is positive, my 270-degree value is negative compared to the zero. Beyond the peak values and the zero values, every other point along that line represents some sort of voltage, and every point along that line is considered to be an instantaneous value, meaning that is the value of that instant in time when our generator passes that point. If you're to throw a dart at a sine wave and hit it along the line anywhere, you should be able to calculate exactly what the instantaneous value of that sine wave is by understanding the fact that represents the sine value of the angle of which the conductor is. Our formula for this is E is equal to E max times the sine of theta. Now since our peak value or our E max value is the length of our entire phasor all the way up, which creates our maximum possible generation, if we take our E max, which would be the same as saying our hypotenuse, multiplied by the sine of the angle that we're operating at, we will get the vertical aspect. So we're going back into trigonometry again. Consider this sine wave we have on the screen. If E instantaneous, which is represented by the lowercase e, is equal to E maximum, which in this case is 10 volts, multiplied by the sine of the angle, I can predict what every voltage is all the way along that, from 1 degree all the way to 359 degrees. For the first example, I have my E max at 10 volts multiplied by the sine of 20 degrees gives me a value of 3.42 volts. So at 20 degrees rotation, I should have a 3.42 volt value. And that's how much voltage is being generated at that exact moment in time, which is why it's called the instantaneous value. If I were to look at the opposite side of the sine wave in the second alternation, I can see at 210 degrees, if I took the sine of 210 multiplied by 10 volts, I would end up with 5 volts. So that exact point in time in the rotation, I'm producing negative 5 volts because I'm on the second side of the rotation. Therefore, it's a negative. And I'm also at 210 degrees, so the sine of 210 would also produce a negative value. Keep this in mind anytime that you're working with instantaneous values. Every spot on that cycle can be calculated. Even the peak cycle, which would be E max times sine of 90 degrees, which would be 10 times 1, means that the instant value at peak is 10 volts. Another term that we need to get used to is called the effective or the RMS value. If you've ever been shopping for an electrical meter, you'll know that the electrical meters will read an RMS value, usually considered to be called the true RMS value. RMS stands for the root mean square value, which means it's the root mean of the square of each sine all the way along the sine wave. What this gives us is an average. When you consider looking at a sine wave, we only see a peak value twice during the entire cycle. That means the peak value doesn't really do us very good at all. The rest of the time, we're at some operation below peak. So when we look at a circuit with our electrical meter and it reads 120 volts, that's not our peak value. That's considered our RMS value, which is our average value of that entire sine wave. The RMS value is the instantaneous value of the sine wave at 45 degrees, which means that if we do have our RMS value from our readings, we can calculate what our maximum value is going to be and vice versa. We can calculate Emax using our RMS by having Emax is equal to ERMS divided by 0.707, which is the same thing as sine 45. It also works if we take Emax is equal to ERMS multiplied by root 2, which is 1.414. Both of those equations work. Myself, I find it easier to remember that ERMS operates at 45 degrees. Therefore, if I just do my instantaneous calculation, I'll get the same answer. That ends part 3 of this module. Please return to the blackboard, complete the knowledge check as well as the exercise sheet, and then continue on to part 4.